Hi. Um, okay, so let's go through the entire procedure of how to model a pipe underneath soil step by step. Um, it's gonna look like that. It's what I've done previously. So I think it should be valuable for you to look at this video and go through my steps. And if your model have anything different with this, it should be minor. So I have already opened this model here called video example. So first thing first, what you should do is to set work directory from file menu. And here is where you specify your preferred work directory. Okay, after that, select file, save as, save this CAE file. It's a model database file. Okay. So as you can see, the CAE file is somewhere here. Here it is. So the first step to start a ABAQUS modeling is to create parts. Parts are like, well, components that you can use repeatedly. First, create pipe in 3D, deformable, shell, and we are using sweep. Here is the area you see what you are going to do next, instructed by the program. So here it says pick a starting point of the line. So we draw exactly what we want. Create arc. And then create another straight line. Another arc. Finally, the long straight segment of the pipe. Then we have to prescribe dimensions to our pipe. That's the pass. Oh, mind you, as we've said before, you have to first determine a system of unit convention by yourself and follow that throughout your modeling. So that's what I determined. Forces in kilonewton. So other units change accordingly. So let's say this is 1 meter. Say 3 meter. 10 meters. And the radius of this elbow, let's say, well, since the diameter of our pipe is gonna be 0.3 meters, so let's say the elbow radius is 0.45. 0.45. Great. So that's that done. Sketch the sweep path done. It says enter maximum scale of the section sketch. The section will be diameter 30.3 meters and thickness of 10 millimeters. So we don't need that big, probably 5. It's a circular section. Again, assign dimension. Would be 0.3 of a meter. That's the radius, so it's 0.15 of a meter. That's done. Second part would be soil. 3D deformable solid extrusion. It's about 10 meters long. Sketch the section of solid extrusion. So it will be like a squared section. Remember that the diameter of the pipe is only just 0.3, so perhaps the length of this square of this line will be 5 times of the dimension of the pipe. So that's 1.5 meters. One point five. Okay. So here this small window pops up. Type blind. Depth, let's say 15 meters. Make it slightly longer than the straight part of the pipe, so that we have space for the elbow. So because we are modeling explicitly the contact between soil and pipe, we need to dig holes in this solid thing. That can be done by this button, which is called Create Cut, Extrude. Yeah. Select a plane for the extruded cut. Okay, so we need a plane first. It's on the YZ plane, offset 0. Okay, it's not exactly in the center. So perhaps we can do it in another way. Create a plane by 3 points. So we make sure it's in the center, at the center of this solid entity. Here we are. Now what we are going to do is to sketch the path of this cut so it's not right. Right? Sweep. We have to create cut from sweep. So sketch the path and the profile of the cut. But remember that in order for the contact algorithm to work perfectly, the sketch should be exactly the shape of the pipe. And now what we need is to go back to the pipe part and select Path Sketch. There will be a button here called Save Sketch as Pipe Sketch. Is it there? Yes, sketches. This is our sketch. Then go to soil part. Create cut by sweep. Path sketch. Select the plane for the sweep path. That's that. And the button right next to the Save Sketch As is the Add Sketch. Here it is, our sketch. say translate here to somewhere here. We haven't got a reference point. We haven't got a reference point on this thing, so we need to add one. This function is create datum point in the midway between 2 points. That's what we want. So here is our datum point. Now we try this again. Yeah. Translate the pipe to the place where it's meant to be. Done. Done. This arrow here indicates the way, the direction of the sweep. So is this direction of sweep correct? Is it? Yeah. Yes. And then profile. Profile also should be exactly the profile we have just prescribed with our pipe. But that's simple. That's just a 0.15 radius circle. Yep. Done. That's all done. Options. Don't need that, don't need that, don't need that. Perfect. And now we have it done. As you can see, this is toggle global translucency. Don't know what that means, but it shows through the solid body. Okay. Next thing, with the shape ready, next thing is to prescribe material properties. So for the pipe section assignments, select the regions to be assigned a section. Pipe. Select all of it. Region, pipe, section. We need to define a section. Pipe section. So it'll be solid, homogeneous, check. And name pipe section, type solid, homogeneous. Material, we need to define a material. Pipe material. Material behaviors, general density, and I also have these material properties ready. So we will have a bilinear steel, for example, 7.85 of density. That's in the unit of ton per cubic meters. And the Young's modulus, the elastic properties, Young's modulus and Poisson's ratio. In elasticity, elastic. Copy it. Type isotropic, just isotropic. And plastic properties. Mechanical plasticity, plastic. Copy. Right. So pipe material, yes. Okay. Section. What? What's wrong here? Apparently something went wrong. Why is that? Because it's solid homogeneous. But what we have here is a shell part. So that's wrong. Delete it. Do it again. Pipe. Done. Region pipe section. Create a shell section homogeneous for pipe. Great. There you see there's a significant difference here. Thickness. We should define the thickness of our pipe here, which is 10 millimeters, which is 0.01 meters. That's not relevant, not relevant. Pipe material, yes. Thickness integration points at least 5, so 5 will be okay. Section integration during analysis, okay. Nothing needs to be changed. Great. And shell offset. That determines whether the thickness will be counted starting from the inside or starting from the outside. In your case, you need to, well, double check after you've done it, but I know here it will be bottom surface. Let's see whether it's nicely done. From here, it's just a shell because the thickness of the shell is not reflected yet. If you select View, Part Display Options, and Idealizations, yes, you can see Render Beam Profiles and Render Shell Thickness. If you apply it, yes, that's what we want. So we leave it like default. Oh, great. It's done. And for soil section assignments, soil, the whole soil. This time we need a solid section because it's solid. Soil section. Solid homogeneous, no problem. New material for soil. Of course, we have material properties here. Let's use this one. The damping, the value of alpha and beta of the Rayleigh damping can only be determined after you run a eigenvalue analysis. So let's just assume no damping there. You can assign it later. With density of 2, density 2, and elastic properties. So it's like a very simplified configuration. But any plasticity model of the soil is gonna consume a lot of computational resources. So it's gonna be very time consuming. Unless you run it on a supercomputer, it's never gonna end on your own laptop or PC. So yeah, that's done. What? Okay. Can't have the space there. Soil material. Right. Soil section. Right. Great. Apparently our parts are already done here. Of course they are not meshed yet, but I suggest you to leave the meshing in the end of your modeling, because every time if you change your configuration of the part, the mesh is gonna be deleted. So no point doing it too early. So this is effectively a checklist here on the left hand side of the screen. So parts done, materials was already done, sections done, profiles not relevant. In this case, profile is for beams, for beam elements. So now we are heading to the assembly section. assembly section is basically where you put your ready-made components, put them together to build your actual model. So the actual model is built here. These are the parts, is effectively just a library of components which you are gonna be using in the assembly section. From this bottom here, the very first one is create instance. Instance is just the parts you've modeled. So pipe, both pipe and soil, and instant type dependent mesh on part. So we can mesh, well, build the mesh on the part rather than the assembly, which is better. Okay. So obviously we need to do something to put them in the right place. So let's say we need to use these two functions apparently. This one is translate instance and this one is rotate instance. Let's rotate it. Select instance. Okay. And select the axis of which your instance is about to rotate against. $90 degrees? Yes. Okay. Translate the pipe. To the middle of soil. Great. Yeah, we have a shape of it. It's probably a good time to click save now. So two instances are in place. Features, that doesn't matter. Engineering features. You can specify a point of masses or springs and dashboards from here. Okay. And for the time being, let's not bog down by the steps because we are not finished here. We still have interactions, constraints, loads, and boundary conditions to go. So yeah, interactions. This is where we specify interactions between the pipe, the external surface of pipe, and internal surface of soil. So we have soil, pipe, soil, interaction. You can either use a general contact or a surface-to-surface contact. I'm gonna use a surface-to-surface contact here just for demonstration. You can try another one. Alright, select the master surface. The master surface will obviously be the internal surface of soil. So you can select either from here or you can define a set previously from the part and then select faces from here. Let's show that. I'm gonna doing that way. So from pipe, the parts, pipe, surfaces. Double click surfaces and external surface of pipe. Geometry. Continue. Select the regions of the surface. This. And you can see it's brown in the interior and purple in the exterior. So we want purple here. For convenience, we can also define an internal surface that we will be using to put internal pressures on. So this time it will be brown surface, which is the internal surface. Great. So soil is the same story. Soil, internal soil. It's a bit difficult. But you can always use these functions to make life easier. Great. So create interaction. Surf-to-surf contact, standard. Select surfaces here. The master surface will be the internal surface of soil. This one. Check if it's okay, yes. And choose the slave type will be surface. The external surface pipe. Yeah. So here we are, this edit interaction window pops up. Name, pipe soil, type surf to surf. Step from the initial step, no problem. Master surface, internal of soil, external of pipe, as a slave surface. Sliding formulation, finite sliding, yes, if it's relatively large. If the displacement of sliding is relatively large compared to the size of the mesh. So finite sliding it is. Discretized method surf to surf. Don't need to change that. Slave adjustment, adjust only to remove overclosure. That's actually, you can either select this or this, not relevant. Not changing anything here, no. And here we have to define contact interaction property. Type soil contact. Continue. So obviously the simplest way of defining contact is tangential behavior plus normal behavior. So we will have one of this and one of this. The tangent behavior is frankly where you just put a coefficient of friction in. So the simplest way is penalty, where you have a friction coefficient. Could be any value you want that's reasonable. Say 0.5. Yes. And then normal behavior, hard contact, simplest way of defining normal behavior, and leave as default. Right. Just leave everything else as what they are and click OK. So that's done. No need to do that. No need to do that. No need to do that. Constraints. Constraints is where, well, for instance, we have this section here, which in my case is expected to, let's say, fixed on a reaction wall. So we need to prescribe set the behavior of the nodes on this ring to one point and fix it. So we give it a name, ring at flange. Ring and flange. Type rigid body, And as you can see, there are many other types you can use, which are all quite useful, depending what you're looking for. If it's like a coupling, it's for where you link the kinematic behavior or response of one point to another point. And equation is very useful for modeling 2D site response analysis and so on. But here we are just using rigid body constraint. We have a tie here, which goes to this ring flange. Yes. And we constrain the movement of this area to a reference point somewhere in the center, probably. Prescribe a reference point here. Great. And select it. So you can see it's point picked. Maybe you want to give a name to it. But anyway, it's the same. Right. And loads and boundary conditions, because the loads and boundary conditions are pretty much, well, let's say, gonna change in different steps. So probably we should go with steps first. Steps, as you can see, it's got a initial steps, which is, well, kind of standard for all analysis, and you don't have to be bothered with it. We create another step according to what we need. Say first, let's give it a linear perturbation frequency. Let's give it a eigenvalue analysis. Eigenvalue analysis. Continue. So this is where you edit your step. Name eigen type frequency, basic nonlinear geometry off, because it's a linear perturbation, so it's naturally off. Well, yeah. Eigensolver, don't have to change this. Number of eigenvalues requested, could be all frequency range or like 10 probably. Just leave it like that, it'll be fine. With eigenvalue analysis done, let's go to a gravity analysis. Gravity. It's rather like a static step where you're gonna apply both gravity and pressure. Yeah, right. So procedure type general, static general, name gravity type static general, basic, time description, time period 1, nonlinear geometry, yes on. That's incrementation, automatic, fixed. You can have one, but if you experience some difficulties in say difficulties in convergence, probably you can set that to some smaller numbers and put that value, put this number bigger, to ensure that it's not because of this that the analysis stops. That's pretty much everything you need to know. Okay. And then after the gravity analysis, it depends on what you want, really. If you want a static analysis that reflects buckling of pipe, then what you need is a static Rix step. It can analyze the unstable behavior after the yielding point or whatever stabilized point. So if you want a buckle, you want to see buckle on the static analysis on the pipe, you have to choose this. But if your mind is in conducting a dynamic analysis, then it's just simply dynamic implicit. Let's say, take the static analysis for an example. So static rigs. Great. Static rigs. Nonlinear geometry on. Stopping criteria. This is the nature of this algorithm. So what you're gonna do is click either of them. Say maximum displacement. I want the test to stop at a certain displacement on a certain point, on a certain node of my model. So let's say 0.1, maybe 0.3, like a little larger. Say this point here. So what I'm gonna do firstly is to fix the pipe here and say let's move the entire body of soil on the negative direction of x-axis to see what kind of damage the pipe or the elbow is gonna take. So we prescribe a 0.3 meter displacement from this direction. So the dot would be 1. That's the translate movement on the x direction. Node region would be, seems you have to define node region first. Define node here. But actually, alternatively, it's easier to prescribe a maximum load proportionality factor, just set by 1. So if it's 1, the test will stop automatically when the prescribed 0.3 displacement is applied. So that's easier actually. Then incrementation, because it is, well, nonlinear analysis, as you can see from here. Nonlinear geometry on. So you do not expect it to finish in one step, right? So probably it's gonna finish in 1,000 steps, I don't know. Let's say the initial arc length increment is 0.01 and we allow it to go down as far as 1 times e to the minus 6, and the maximum is restrained at 0.01. So hopefully it's gonna go steadily in increments of 0.01. And estimate total arc length 1, that's just fine. Others, not much to concern about. Yes, great. Okay, so that's our steps done. If you want otherwise, if you want a dynamic analysis, you cannot prescribe a dynamic analysis after the risk analysis. So what you're gonna do is probably suppress this step and have a new dynamic implicit step right after the gravity analysis. But here, we're just gonna keep it like that. Okay. How long is this video now? Okay, initially, what kind of boundary conditions do I want to apply? Of course, first things first is to fix this point on the reaction wall. So let's assume it for now is fully fixed. Let's name it flange reaction wall initial geometry displacement. Select regions for the boundary condition. Here. Reaction wall. Done. Name this type correct, step correct, region correct, global, yes. Fix all of them. Fix. Okay. Has been created. Is it? Yes, it is. And of course, we need to fix the soil. And well, let's assume it's a soil box in a lab environment. So we also have to fix this endpoint as well. That means we have to constrain that end of the pipe as well. So we're gonna do exactly the same thing as we've done before. It's gonna be a ring other end. Yeah. Continue tie. Okay, we need to select the pipe. What I'm gonna do? Replace selected. Instances. Select the pipe. Done. And select the region of the rigid body. Ring other end. Yeah, done. Point another reference point at the center of the section. Yes. Select the reference point. That one. Yeah. Yes. Selected. No problem. Double check if it's correct. Yes, it is. Yes, they are both correct. And let's go to the basis of the soil. We have perhaps 4 boundary conditions. One is the base of the soil. Number 2, the x-axis surfaces of the soil. This one and this one. And number 3, the x-axis of the soil surfaces. This one and that one. And finally, the pipe end. So let's start with the base. Soil base. Category mechanical step initial. Check type of boundary condition displacement. Continue. Select region. It's a surface. It's soil base surf. Oops. Done. Fixed. Okay. Soil Z surface. Check. Oops. Press Shift when you want to select multiple things. So soil Z surface. Done. What kind of boundary constraints we have to apply here? We should restrain it to move against X directions, so the soil body can expand. Right? Yes. Soil X serves, check. Soil X serves. And for this, it's not able to move at that direction, U3. Yes. Type ascend. Initial mechanical displacement. We had a set. Oh no, we didn't have a set. Select RP2. Select it. Done. Type other end, displacement, rotation, initial, region picked, global. It's not able to move. It's not able to move at the X direction. Right. You can also, well, considering have a sort of spring here to simulate the infinitely long pipe, straight pipe. Or maybe have some beams, have some beam elements and some springs on the beam element to simulate soil pipes interaction on the less important areas of the pipe. Okay. Then obviously it's just the initial boundary condition. At the eigenanalysis, it's not relevant. It's just keeping the initial boundary conditions, so it's okay. And gravity, at gravity step, we need loads, and perhaps and the boundary conditions will still be the same. Let's define the loads. So first thing first is of course gravity. Category mechanical, step gravity. Types, we have gravity ready here for us. Okay, so edit load, name gravity, type gravity, step gravity, region, whole model, that's fine. Distribution, uniform, fine. And yeah. As you can see, the y-axis is here, which means the direction of gravity is minus y-axis. So minus 9.81. Why is 9.81? Because the unit here for acceleration is meter per square second. So if your unit of acceleration is in g, then it would be 1. But if it's meter per square second, it'd be 9.81. Amplitude, ramp, it's okay. Okay. As you can see, this arrow here shows up indicating the gravity and load has been assigned properly. And following is of course pressure, internal pressure, PRESSURE, pressure of the pipe. Pipe internal pressure. And also there is an item of pressure here ready for us. That's great. So select the source of the load, which if you remember we have just defined it before minutes ago. Pipe internal surface. Yes, correct. Pipe internal pressure, gravity step, region, that's correct. Distribution, that's correct. Magnitude. Well, the unit of pressure would be kPa, kilopascal. So let's have, say, 1 megapascal. 1 megapascal would be 1,000 kilopascal. So 1,000 here. Okay. And these pink arrows shows up. Great. And finally, the steps, the boundary condition in rig step. In here, as I have stated previously, what we want is a uniform displacement of soil from the positive x direction to the negative x direction. So basically, it's moving that way. It's moving that way, and bend the elbow. Bend the elbow pretty much if the displacement magnitude is large enough, surely you will see some damage here and even perhaps here, although this bit is constrained by soil. So what we need is an extra boundary condition to prescribe displacement of soil, and we also have to modify our previous boundary conditions to allow the new boundary conditions to be applied. So firstly, it's the displacement of soil in the rigs step. Check. But it could also be acceleration, you know, if it's a dynamic analysis. But here, since it's static, we don't have acceleration here. The whole of soil geometry, yeah. Well, actually, if we are simulating the flexibility of soil, you know, in a soil tank, maybe what you want is to just prescribe this displacement at the 5 boundaries of this box rather than the entire soil. That would be more realistic, but here it's just a demonstration, so I'll just leave it like that. Soil, highlighted, yes. Continue, yes. Name, great. Type, displacement, okay. Step, okay. Region, okay. Global, coordinate. Method, specify distribution uniform, and U1 minus 0.3. It is minus because the coordinate system we have selected is a global coordinate system, which is here. And you can see if it's positive, then it's going that way, further from us. But we wish to go the other direction, so it's a minus sign here, minus 0.3. Okay. And you can see these arrows here all over the soil body. And because it's moving this direction, it clashes with some of our previously defined boundary conditions. So we need to modify them. For instance, this one, soil base, is no longer have to be restrained. So this unselected, you can see that there is a star here. It says modified in this step. Okay, so it shows modified. And let's check if the other boundary conditions needs to be modified as well. This one, yes, they are. They are just this one. Okay. So since it's only one, it's the constraint at U1 is the only condition applied in this boundary condition. You are not allowed to unselect it. What you want to do is to deactivate it completely in this step. So it's inactive now. Yes. So this is still fixed. Great. the other end moves together with the soil box. So this needs to be modified too. Great. Soil base unselected. Leave it like that for the X serves, and this is inactive. That's done. So that's pretty much everything we have here. Oh yeah, field output requests. And you can define either through here or through the steps module, where you can specify a field output request for each step. So we can see the field output 2 is what we mostly concerned about for the gravity analysis and risk analysis. So we're going to modify that. Of course, you cannot have all of them because otherwise your output database, which is .obd file, will be extremely large and extremely slow to open. So for contact, perhaps what you need is contact status, forces and rotations. Nodal forces is probably what you want for extra. Displacement, that's fine. Strains, equivalent plastic strain, logarithmic strain, or perhaps inelastic strain. Yes. Stresses, that's basically depends on what you want. I'm also not really sure what all of these are for some of these, but you just need to know what you want. And so that's pretty much that. So are we quite finished here? So what we left is doing the mesh, I think. You may have remembered that we made the instances a dependent instance, which means the mesh will come from the part. So we are now meshing the part instead of assembly. Part, pipe, soil, right? For pipe, it's very easy. What you need to do is just first partition it in half. Yes. Create face, surface, and slice the pipe in half. Face, create partition is this bottom. Create partition, type face, method, using datum plane, select it, or select the face. Select the faces, good. Select datum plane, good. Create partition, good. So it's partitioned, as you can see, beautifully. And then what you need to do is create seeds. Seed is basically how you're gonna have your mesh modeled. How dense it is it biased or not? Some things such like that. You have a global seed or a local seed. Seed edges is local seed, and globally is seed part. So we first seed it globally. Say we want to approximate mesh size of 0.5 meters. Okay. And as you can see, it's a very coarse way of seeding this part, and probably We can modify it to something much smaller. Much smaller. Okay. Because on the at the hoop direction of circumferential direction, is that the word, of the pipe, you need to have enough mesh, enough number of elements in order to reflect the actual buckling of the pipe. So it's good to have more, given that your computer allows you to have as many as you want. And perhaps on the straight pipe, which is less significant, we probably need a coarse size of mesh. Say even 1 meters. That's maybe too much, too big. Element size. Okay. Why don't we bias it? Bias single minimum size, maximum size, flip. You can see the direction of bias here. So it's all right now. It's all right now. Okay, as you can see, the seed here is more dense, more refined than the other end, which is exactly what we want. And I can show you a double bias. Double bias is basically, well, you can imagine. Yeah. Yeah. Finally, since I'm not actually gonna run it, so I can go crazy here and put everything in very small number. But for you, if you're gonna run it, you're gonna have to, well, try to run a validation test to see what kind of mesh is appropriate to give you a very reasonable analysis result, and at the same time without costing you too much time. So that's done. Assign element type mesh on shoe. I think we can just simply mesh it. Now, okay to mesh path, yes. Mesh path is meshed. And from this button, it says S4R, which is the type of element, coincidentally, what we are going to use for the pipe. Assign element type, select all of it. And yeah, it's S4R already. So it's standard element, linear geometry, shell family, shell element, a quad element with reduced integration. Sounds good. A 4-node doubly curved, sing-all, 6 shell, reduced integration, hourglass control. I don't know what that means, but it's better to have that. Finite membrane strings, great. So that's done. That's that done. Let's go to soil. For soil, it's a much more complicated story. If you have an elbow, particularly in your soil, it's going to be very, very difficult. But if you have just a straight pipe, it's very easy. So there's actually a lot of partitioning to do with soil. It's going to be quite difficult, but I think it's better to find out now. What am I going to do? What am I going to do? So start with the basics. Apparently, whenever the geometry is too complicated, the software is unable to mesh it. So the principle here is to make the geometry of a single cell as simple as possible. Yeah, with that in mind, we have to create some faces, some datum planes actually. Sorry, some datum planes. Y-X, okay, and offset. Create datum plane offset from plane. So offset from this plane, from, oh my god, from this plane to here. Principal plane from which offset? X, Y, X, Z, X, Z, X, Z. Offset from here to here. Great. And offset from here to here. Sorry, I don't want to sound like pig, but that's what I sound when I get really confused. Offset. Do I need to position it here? Seems not. First things first, it should be split in half, like in the same way as I did to the pipe. Yes. So partition cell using datum plane. Select it. Yes. Create partition. And then, because this part is a complicated geometry, it's definitely gonna be sliced in half here as well. Select the cells to partition, all of it, and using this datum plane, create. Good. The different color here stands for the different meshing techniques that ABAQUS is able to apply to this certain geometry. So what you're gonna see from here is assign mesh controls. Yes. Basically, you can see a number of colors indicated here. Basically, green is the perfect, is what we want. Sweep is okay. Bottom up is not what you really want. And sometimes you need to use a different shape of element. For instance, a hex is basically a squared element. But if you want an element with 4 faces, it's TED. Well, use it only when you have to, because it's not very accurate in its result. So yeah, not very accurate. And certainly it should be sliced in half here. Here, these two cells. Okay, and this starting plane. Okay. Okay. Yes, that's exactly what we want. And from here, these two cells should be partitioned from here. Create partition. Okay, what am I gonna do with this? Apparently, it should be partitioned here along its center line to make it two pieces. One here, a quarter of a circle, and the rest here. Okay, so partition. How to partition face? Use curved paths between two normal edges. Normal to two edges. Select a face to partition. This face. How do you want to specify the end regions? Pick. Select an edge on the. Okay, here, pick a point. Here. Select another edge. Here. Pick a point. That's not a point on the edge. Okay. So first I'm gonna have a reflection of the position of the center line. So a datum plane is underway. Datum plane is certainly underway here. Yeah. Face using curved paths normal to two edges. Can I do it now? No. So what if I first partition this face? And give it a point here. Pick this edge. Oh, great. Yes, create partition. Yes. So the face is partitioned. Then cell extrude sweep edges. Select the cells to partition. These two. Okay. Select one or more edges in the same plane to sweep. Done. How do you want to sweep? Sweep along edge. Select an edge to define the sweep path. Okay, that direction. Okay, create partition. Great. Oh. Is it not partitioned? Okay. So the right hand side is done, left hand side is not done, apparently. So it has to be done a similar way again. Very boring. Very boring. Oh, sorry. How I pick the edge? This one here. This edge, endpoint, create partition. and then partition cell using extrude and sweep edges. Select edges, select cell, this one, this cell. Continue, select one or more edges, this edge. Done. How do you want to sweep? Sweep along an edge, this edge, yeah. Yes. Oh, yes. Okay, for these top blocks, we should probably partition it two. Basically, how you're gonna partition it is totally down to your personal preferences. But well, the principle is the same as I said before. It's just to make every and each single cell as simple as possible on shape. Probably for this to have great. And it's a 90-degree bend, so it's still relatively easy. Imagine it's a 45-degree bend, it's gonna be much more difficult. It could take you hours or days to do the meshing actually. So right. Normally experience told me that these two is not possible to model through a hex structured element. I need this. So yes, probably that's it. Let's try out. Let's try out. These buttons are available for you, well, for you to have a better view over your model. Especially when you are seeding it. It's very useful. Very useful. No. Alright, this warning will pop up when you have two different two different techniques of meshing, because you may remember I selected TED elements. for this region. So it shows the highlighted faces represent interfaces between regions that will be matched with incompatible element shapes. You may continue to mesh and create an incompatible mesh. Tie constraint will be generated automatically or cancelled meshing. So it's okay. It's been, well, this kind of mesh is being used in mechanical by mechanical engineers, well, quite frequently, this 4-phase element. So it's fine. And to be honest, I have to use this kind of mesh. So obviously something here is not right. Something here is not alright. And the rest of it seems reasonable. Here seems reasonable. And probably sometimes you want to cut it through somewhere in between to inspect if your mesh is good in between in the middle of a cell of a solid body. Say select entities. Let's select elements to remove. Select elements to remove these and see from the middle, from inside of the soil body. It's okay. It's very nice actually here. It's very nice here. Apparently here it's just not okay. Not okay. If it's not okay, you're gonna delete your mesh, right? And further partitioning your assembly, your part. Sorry. Further partitioning. Say let's let it move 1.5 meter, 1.5 meters. Yeah, great. And then partition it. Cell, use datum plane, all of these cells. Partition by this datum plane, and yes. Okay, and seed. What will that do? Try out. See if that will do. Still not entirely reasonable. Still not entirely reasonable. That could have something to do with meshing technique. Perhaps if I change it to sweep. Some regions cannot be swept. Okay. Okay. You see, because these seeds are biased, but the length of this edge and this edge is not equivalent. So the mesh is gonna be odd. So what should I do? So I have more seeds on these edges. More seeds on these edges. More seeds on these edges. So let's do it by number. Probably 25. And for this, let's give it maybe 30. Is it gonna be alright? No. Perhaps I should not bias it at all. And assign it by size so that it will automatically have the different number of seeds according to their length. That's perfect. Is that okay? Yeah, that's more like it. That's more like it. Oh, and something is wrong here. Fuck. Sorry. Let's not bias it. It seems like it's been problematic when I did it previously, and it is now also quite problematic. I'll leave it to you to try out. Yes, finally, yeah, finally. That's more or less okay. A very good way to examine your meshing is to use this function, verify mesh. Okay, so select the regions to verify by part, the entire part, and analysis checks. Color key errors, warnings, highlight. You can see. So it's not okay. Your analysis will definitely be aborted because of this. So what you're gonna do is refine the mesh little by little until all of these are gone. Okay, I'm not gonna show this here because it's getting too long, this video, and it's quite boring. But yeah, I have done this before, and it took me like many hours, 2 or 3 hours, 3-4 hours even, to get rid of all of this. And once you have it ready, you can use it for the entire analysis of your research. So it's a one-off job. It's kind of fine. So yeah, that's pretty much it. I think I can say that's it. So then what you're gonna do is create a job here. Of course, it's not gonna run for the first time. Trust me, it's not gonna run. And what you're gonna do is to right-click your job and select monitor. Okay, so here you have extensive number of informations that I might need, errors, warnings. So as you can see, a lot of messages will pop up during your analysis. Some of them are actually quite irrelevant. For instance, these messages are from the tie constraints that the program automatically applied when we had different mesh shapes, if you remember. So that's irrelevant. Output request is not available for this type of elements, so that's irrelevant as well. Irrelevant. Over constraint checks, that's irrelevant as well, to be honest. But some of the messages is the key for you to find out where your modeling went wrong. So mind that, and especially from the error, right? Yeah. So that's basically that. That's basically the modeling of pipe and soil. buried underneath soil. And when one of your job is finished, right click the job, go to results. This is one I done previously, a similar model. So make sure you have selected this ODB and see the contour. It shows you basically everything you need. Everything here is prescribed by you from the field output request. So you have to well, basically know what you want to see after the analysis and prescribe it. This is an example of showing context status. For example, if you click here and unselect one of the instance, you can see it's an indicator of the contact algorithm is working. It's very good. So it's just a gravity analysis. You can see from 0, from nothing, well, to at least something, although here it's not in context for some reason. Right. What else? What else do I need to tell you? Results. How you gonna see the results from create XY data here? So usually it's a field output, and you can select the step you want. Either it's from a gravity step, or it's from a rig step, or a dynamic step, and you select and unselect it from here, and change the output variables to a position of unique nodal, which is the node on the mesh, and select the output variable you want, say the value of displacement at x for here is z direction, so you use 3, this direction, and which node you want, method pick from viewpoint, add it, and have it say here at the top of the column. It's a bit difficult to see. You can save plot, you can save it, it's saved. From here you will be able to see a plot of it. Alright. And if you want to plot a relative displacement between 2 points, and you have to do this twice from this point, or say another point here at the end of the other pipe end, and then you click operate on XY data, and you have 2 variables, 2 set of data here, and you can this minus the other one, and there's a number of, well, predefined functions for you there, which is all very useful. The normal add, minus, multiply, and so on. And this combine function is for you to plot something on a 2D plot. So you have one data set on the x-axis and another data set on the y-axis. Pretty useful, this function. And you can see the result of this calculation, and let's say +2 plot expression. So it's a 2 line, a straight line of 2. Great. What else? So for pipe, there is also another very useful stuff. Is create free body cut. So this is for you to inspect an actual force and moment on the pipe section. So pipe section 1. Okay, based on view cut, 2D, 2D, 3D elements and nodes. So for instance, I want to see the actual force and bending moment on this section located here. Method, pick from viewpoint, select elements for display group, elements, and select nodes, 50 elements. Great, reasonable number. Yep, what happened? Okay. And the node, for instance, on the right hand side of this view cut, okay. And you can see at free body cut, summation point, centroid of cut, nodal average, user defined. That's just depend on you, what you want. Normal and tangential, global coordinate system, okay. Yeah, and that's that. So I think you'll be able to you'll be able to extract data points from the free body. So create XY data and select free body. Select the step you want. Select the entity you want, force, displacement on the axial direction. So that be in the global coordinate system, the Z direction, that one. Of course, you can have the magnitudes, plot, yeah, and that's it. That's it. So you can see the force developing and the moment developing, the graph. After that, finally, animation. You probably wanna, whenever one of your model is finished, the most easy way for you to inspect it is of course graphically through an animation. So animate time history. You can see it's just a time history of applying gravity loading. So it's quite pointless. But if you have a dynamic analysis, it's very useful. This is animation options. You can have play once, and you can let the frame pass by on a time basis, because at some point when the nonlinearity on the system is severe, you will have more frames in a given period of time, right? If it's linear, it's just gonna be one frame. If it's nonlinear, it has to run many frames, many time steps, therefore many frames. So you're probably gonna select a time-based animation and go for a small number, perhaps. Then you will see it in a normal time scale, let's say. Right. That's pretty much everything you need to know. And as for the presentation of the notations here, select view. Viewport and annotation options, and you can select these off or on. Legend, triad, legend size of the word. 14. It gives you a clear view of the words. And that's the same story for your plot, actually. Because say we are gonna plot anything, any odd plot. Unique nodal. So plot it. You can modify it in the way you like. You can see title. you can have it in a different font, different size. Different size, an axis, you can have it different size. Different size. And you can have a legend as well. The legend can be inside the plot or outside. The background of the plot can be nothing or white or any color. And here is where you prescribe the look of the appearance of your curves. You can have it in red, you can have it in dotted line, and have it very big, like that. So that gives you a quite nice chart. And if you press Ctrl P or simply select print here, you can extract it in PDF or in some other format you want. Normally, let's have PNG. PDF is not available. PNG is good. And you can have a file name. How can I select that? Never mind. Okay. Permission denied. Why? That's ridiculous. Files. ABAQUS. Great. Yes, let's see it. Where was it? Oh my. Okay. It's here. And the good thing about it is if you wanna put it inside a PPT or a Excel file, it's transparent actually. It's not a white background, it's a transparent background, which is fabulous. Yeah. Alright, that would be end of the video.